To solve chemistry problems, first you need to know what the problem is and make a plan. Clarify the known and unknown. Suggest the steps from known to unknown, and prepare a visual summary of steps that includes conversion factors, equations, and known variables. Use a plan as a guidance. Do your calculation and get your solution. Double check if your solution makes sense. In the following, we're going to see some examples how to solve chemistry problems. Let's look at sample problem 1.3. To wire your stereo equipment, you need 325 centimeters of speaker wire that sells for 15 cents per foot. What is the price of the wire? So first you need to identify what are the knowns and unknowns and what is the goal of this problem. So one of the knowns is 325 centimeter in length. Okay, so first the length is 325 in centimeter. That's one known. The other one is the price is 15 cents per foot. Okay, so two knowns. The unknown is the price of the wire we want to solve. Okay, we want to solve how much price, how many dollars for this wire. Okay, so first let's look at the length units. Given is a centimeter, but the price is dollar per foot. Okay, even though these both are units of the length, but they are in different systems. One is in SI unit, one is in English unit. So first we need to make a conversion from centimeter to foot. Okay, so we go back to the table we shown before, which is the common SI English equivalent quantities. In 8th edition is table 1.4. Okay, from that table you will see one conversion between English and SI unit is 1 centimeter equals 2.54 inch. Oh, sorry, 1 inch. Sorry, 1 inch, 2.54 centimeter. Okay, using this as a conversion factor, we first convert centimeter, so centimeter to inch. That's one first step. And then because we want to change to feet, so we have another conversion factor that is 1 foot equals 12 inch. All right, so that's within English units. And so using this as a conversion factor, we change inch to foot. Okay, so now the length is in foot, and then use this price as a conversion factor. We can change from foot to dollar. Okay, so here is our plan. First, the length unit centimeter goes to inch, and then from inch to foot. All right, so now the price unit is consistent, both are foot. So now use this price as a conversion factor, we can change to dollar. Now, if you have a conversion factor from centimeter to feet directly, then you can use that one, okay, instead of using two steps. And then from foot to dollar, okay? We'll see in the next slide how we make the calculations. We already have a plan, and that is to change length unit from centimeter to inch, and then inch to foot, feet, and from feet to dollar. Okay, so we always start with the known value, and in this case is 325 centimeter, which is given. So that's the number we start with, and then we multiply by a conversion factor. Okay, we want to remove centimeter. We want to replace centimeter by inch. So we look at this relationship. We can write two conversion factors. Okay, one is 2.54 centimeter per inch, or we can write 1 inch, 2.54 centimeter. Okay, so two possible conversion factor. Now, which one do we choose? We choose the one that we can cancel centimeter, and inch will be the final unit. So to do that, we have to choose the second one. So here we use 2.54 centimeter as the denominator. So unit centimeter cancel. The inch is the final unit. And then the numbers, we can combine 325 divided by 2.54, give you 128 inch. Okay, so that's the first step. We already converted the centimeter, 325 centimeter. Now we know it is 128 inch. Okay, so next step, we start with 128 inch. Okay, and we want to again cancel inch. We should get foot. All right, so here is the relationship. And again, we have two ways to write it because we want to cancel inch. So we put inch as the denominator. So 1 foot is equivalent to 12 inch. So by doing that, cancel inch, and foot is the final unit. So we have 128 divided by 12 give you 10.7 feet. Okay, next, all right, we start with this number now because this is the known number at this moment. So 10.7 feet. Okay, that's the starting point, and we want to change to dollar, and this is the relationship. So there are two ways to write the conversion factor. One is 1 foot cost $0.15. Okay, the other way to write is $0.15 can buy 1 foot the wire. Which one do we choose? All right, we want to cancel foot, and therefore we use this one. Okay, so write this as a conversion factor. So foot cancel give you dollar, and then 10.7 multiply by 0.15 give you $1.6. Okay, so this question, okay, shows you that we first need to identify knowns, unknowns, and then we make a plan. How do we go from known to unknown? Okay, we may need several conversion factors, several steps. Okay, and then use the plan as a guidance to write conversion factors. Okay, to cancel unknown, unwanted units to get wanted units. Sample problem 1.4. A graduated cylinder contains 19.9 milliliters of water. So here we have a cylinder, okay, with 19, so 19.9 milliliter water. When a small piece of galena, which kind of stone, is added, it sinks. So if you add a stone, the stone goes down, okay, and it will push water up. So now the water goes up to 24.5 milliliter. Okay, so that's the new volume, that's the initial volume, and we can write this is V1 and this is V2. So these are known values. Note that the units are milliliter. What is the volume of the piece of galena in centimeter and liter? Okay, so the volume change from V1 to V2 is due to the stone, the galena. So the volume of galena must be V2 minus V1. So we first need to calculate from by using V2 minus V1, we get the volume, but the volume is in terms of milliliter, and so we need a conversion to go from milliliter to centimeter and to liter. So here is our plan. We first calculate the change of the volume in the cylinder due to the galena. So that's the delta V. Use V2 minus V1. Okay, it's in milliliter, and then conversion from milliliter to centimeter. Okay, there's an important relationship we mentioned in the previous slides, and that is 1 milliliter equals 1 cubic centimeter. Okay, that's an important relationship. Another is 1 milliliter, or you say 1 liter equals 1,000 milliliter. So because milli means 10 to the minus 3, so 1 liter equals 1,000 milliliter. Okay, liter is much greater than milliliter, or 1 milliliter equals 0.001 liter. Okay, so using these relationship, we can convert milliliter to liter. Let's do the calculation. So the volume of the galena is the volume change of the water due to the stone added. So it's from 19.9 to 24.5. The difference is 4.6 milliliter. Okay, now let's convert milliliter to cubic centimeter, and the relationship is 1 milliliter 1 cubic centimeter. So we start with 4.6 milliliter. We write a conversion factor. Since we want to cancel milliliter, so 1 milliliter should be as the denominator. So 1 milliliter 1 cubic centimeter. Milliliter cancel, give you cubic centimeter. 4.6 times 1 give you 4.6 cubic centimeter. So next we want to convert milliliter to liter, and the relation is 1 milliliter equals 10 to the minus 3 liter. Okay, remember liter is much greater, so milliliter is small, it's only 0.001 liter. Okay, and we start with 4.6 milliliter. We want to cancel milliliter, so we put milliliter as the denominator. So 1 milliliter equals 10 to the minus 3 liter. All right, milliliter cancel, give you liter, and 4.6 needs to times 10 to the minus 3 liter. Now we also can write 1 liter equals 1,000 milliliter, right? That's equivalent to this one. But how do we write this as a conversion factor? Okay, so if we use this relationship, so we start with 4.6 milliliter. We write the conversion factor. Since we want to cancel milliliter, so we use 1,000 milliliter. Okay, this is 1,000 milliliter is 1 liter. Okay, again, liter is greater, so 1 liter is 1,000 milliliter. So this way, again, we cancel milliliter. Now the unit is liter, and 4.6 divided by 1,000, and that is the same answer as this one. 4.6 times 10 to the minus 3 give you the same answer. Sample problem 1.5. This question is about optical fiber. Okay, so many times a question has a sentence that is not useful for calculation, so you don't need to spend time on that. If one strand of optical fiber weighs 1.19 times 10 to the minus 3 pound per meter, so this is a useful information. It tells you the relation between meter and pound, the length and the weight. So the question is, what is the mass in kilogram of a cable made of 6 strands, each long enough to link New York and Paris, a distance of 8.94 times 10 to the third power kilometer? So what are given? The given are, we have 6 strands, each of them has a length 8.94 times 10 to the third power kilometer. We also know the relationship between length and the weight in meter and pound. The question is, what is the total mass in kilogram? So the given length is a kilometer. The relation is meter to pound. So first we have to change kilometer to meter. All right, we need to know what is the total length in meter, and then using this as a conversion factor to change to pound, and then from pound we can change to a kilogram. So here is our plan. Okay, we first convert kilometer of one strand into meter. The relationship is 1 kilometer is 1,000 meter, and then from meter change to pound. Okay, so this comes from this relationship, and length to pound. And because we have 6, so we have to calculate the total length in total weight in pound. Okay, finally we convert pound to kilogram. The relation is 1 kilogram 2.205 pound. So this you can find from the table 1.6 in the textbook. So let's calculate. This is our plan. We first convert kilometer to meter. We start with the given value of the length, which is 8.84 times 10 to the third power kilometer for one strand. And we use 1 kilometer 1,000 meter as a conversion factor. We need to cancel kilometer, so kilometer is in a denominator, and which is 1,000 meter, and that gives you meter, and 8.84 times 10 to the third power, and then times 10 to the third power give you 10 to the sixth power. So that is the meter length for the one strand. So next, meter to pound. So this is the conversion factor. So we start with the length in meter, okay, comes from here, and we write the conversion factor because we want to cancel meter. So meter, 1 meter should be denominator, and the numerator is 1.19 10 to the negative third power pounds. And so meter cancel, give you pound. And then the numbers multiply should give you 1.05 times 10 to the fourth power pound. Okay, so next we have 6 of them. So this, okay, we start with this one. This is for one fiber. Okay, we have 6. So one cable, 6 fiber can also write as a conversion factor. One cable is equivalent to 6 fiber. So we can write 1 cable 6 fiber, so that we cancel this fiber, we give the unit per cable. So that means every cable should weigh 6.3 times 10 to the fourth power pound. Okay, so that's the weight, but in pound. And lastly, we need to convert pound to kilogram. And so here, all right, we start with this one and write the conversion factor between kilogram and a pound. And we want to cancel pound, give a kilogram. So pound should be as a denominator. So 1 kilogram 2.205 pound. So pound cancel. Kilogram will be the final unit per cable. All right, and the numbers combine. So here you need to divide by 2.205. So give you 2.06 times 10 to the fourth power kilogram per cable. During the calculation, after we get the pound per strand, okay, so next one is you have 6 of them, so everyone knows you need to multiply by 6. So in the third step, you may just simply write as you times 6, and you give the total pound, and then total pound multiplied by per pound a kilogram per 2.205 pound. So that is okay for simplicity. Okay, so that's one thing I want to mention. The other thing is you can also multiply 6 at the first step, because one strength is 8.84 times 10 to the third power kilometer. So you can times 6, give you total length in kilometer, and then calculate the kilometer to pounds, and then pounds to kilogram. So there's many ways to do it. Sample problem 1.6. A furniture factory needs 31.5 square feet of fabric to upholster one chair. Its Dutch supplier sent the fabric in bolts that hold exactly 200 square meters. How many chairs can be upholstered with 3 bolts of fabric? So what are the knowns and unknowns? Well, first we know that one chair needs 31.5 square feet of fabric. That's one thing. And we know that one bolt that holds 200 square meters, and we have 3 of them. The question is, how many chairs can be upholstered? Okay, so if we look at the unit, one is a square meter, which is for the area, one is a square feet. Okay, therefore we need to convert meter squared to feet squared. Okay, and then from feet squared we can calculate how many chairs. Okay, using this as a conversion factor, because one chair needs 31.5 square feet. So if we know the square feet, then we can calculate how many chairs. But we also need to calculate 3 bolts, how many areas in meters. And so here is a possible plan. We have 3 bolts. We need to calculate, each of them has 200 square meters, so we could calculate total area in meters. That's the first step. Okay, and then meter square must change to feet, square feet. From square feet, then calculate chairs. Now, if you look at the table, textbook table 1.4, okay, and the square, the inch, the English and SI unit, one of them shows that 1 foot equals 0.3048 meter. Okay, but what we want is feet squared and meter squared. Okay, what's the relation between these two? So we need to square both sides. Now when we square the unit, the numbers must square too, and therefore the right side number must square, and that's why you have 0.3048 squared. Okay, don't forget that you square the number, and that gives you 1 foot squared. How many square meter? Okay, so from meter square to feet square, and then how many chairs can be calculated using 31.5. Here is the solution. First, we calculate the total area in meter squared. To do that, we use 3 bolts times 200 meter squared per bolt. That gives you 600 meter squared. That's the total area. And then change it to feet squared, as we shown in the last slide. 1 foot 0.3048. So 1 foot squared should be 0.3048 squared meter squared. Because we want to cancel meter squared, so the left side meter squared should be denominator. So here you times 1 foot squared is 0.3048 squared per meter squared. So cancel meter squared, and you should use numbers 600 divided by 0.3048 squared, and that gives you 6460 square feet. Okay, so next one, how many chairs? Then you write the conversion factor. One chair needs 31.5 square feet. All right, so this is a denominator because you can remove square feet, give you how many chairs. And then 6,460 divided by 31.5 give you 205 chairs. Density is an important property of a substance. It is defined as mass divided by volume. So density can also be used as a conversion factor between volume and mass. If you know volume, you want to calculate the mass, or from mass calculate volume, density is an important conversion factor. This table shows densities of some common substances. Metals usually has high density. Gold has a density 19.3 grams per cubic centimeter. Liquid has a smaller density, for example, water density about 1 gram per cubic centimeter. Gases has very small density. Hydrogen gas, for example, 1 cubic centimeter only have 0.0000899 gram. Here is an example about density. So this is about lithium metal. Okay, you don't need the first sentence. A slab of lithium weighs 1.49 times 10 to the third power milligram. So we have the mass and has sides that are 20.9 milliliter, 11.11 milliliter, 11.9 milliliter. So this gives you the size. And if you have a size, okay, A, B, C, then we can calculate the volume. Is A times B times C. So this allows you to calculate volume, which is milliliter, so you can calculate cubic milliliter. So the question is, what is the density? Now we know density is mass divided by volume. So we have mass, we can calculate volume, all right? So we can calculate density. But the question asks you density in gram per cubic centimeter. What is given is milligram. So you need to convert milligram to gram. And here milliliter, so we need to convert the milliliter to centimeter and then calculate cubic centimeter and then plug in this equation. So here is our plan. First, the mass milligram you need to change to gram, all right? And the length milliliter we change to centimeter, and then we calculate volume in cubic centimeter, and then use the definition equation we can calculate density. Here is the solution. Okay, first we calculate the mass from milligram to gram. So this is given, all right, milligram, and the conversion factor is 1 milligram 10 to the minus 3 gram. Okay, because milli means 10 to the minus 3. All right, so you use milligram as a denominator so that milligram cancel each other, and then 10 to the minus 3, 10 to the 3, 10 to the minus 3 cancel each other, and you get 1.49 gram. Okay, now this conversion factor you can also write 1 gram is 1000 milligram. Okay, always remember milli is smaller than 1, so 1 is 1000, gram is 1000 milligram, or 1 milligram is 10 to the minus 3 gram. So by doing that, you will get the same answer. So next one is we want to calculate volume, but first we need to convert millimeter to centimeter, and the conversion is 1 centimeter 10 milliliter. Okay, or you can write 1 millimeter 0.1 centimeter. Okay, 1 millimeter is smaller than centimeter by 10, so it's 1. So both are correct. Okay, and by doing that, milliliter cancel each other, you get centimeter, and 20.9 divided by 10 give you 2.09 centimeter, or you can write as 1 milliliter, 0.1 centimeter. Here is milliliter, so milliliter cancel. So 20.9 times 0.1 give you 2.09 centimeter. So that's one side. All right. You can do the same for the other two sides, and then calculate the total volume in cubic centimeter. And finally, use mass in grams divided by volume in cubic centimeter, give you the answer. In sample problem 1.7a, we already calculated density. The answer is 0.54 gram per cubic centimeter. In question B, it asks you what is the volume in milliliter of a piece of lithium with a mass 895 milligram. Can you do it? Okay. I suggest you pause the video and try yourself and see if you can do it. Now, this is a typical question to use density as a conversion factor to convert between volume to grams, or between volume to mass, or mass to volume. So here, given is milligram, okay, and the mass. So that's the mass we want to convert to volume using this as a conversion factor. But first, let's look at the unit. Mass in milligram, but density we calculated is in grams. And therefore, first step, you need to convert 895 milligram to how many grams? And then using this as a conversion factor to cubic centimeter. The question asks you in milliliter, and the final step, cubic centimeter to milliliter. Okay, so here is a plan. Right? We start with milligram, change to gram. Okay, then use density conversion factor to change to cubic centimeter, and finally to milliliter. Let's do the calculation. We start with milligram, given 895 milligram. We want to convert to gram, and the conversion factor is milligram, 1 milligram, 10 to the minus 3 gram. Okay, using milligram as the denominator to cancel milligram, give you grams. Okay, so that's the first step. According to our plan, the next step is to calculate the volume, use the density. So the density, we can write two conversion factor. One is cubic centimeter, 1 cubic centimeter, 0.540 gram, or 0.540 gram per cubic centimeter. Which one should we use? Now we start with these grams, and we want to cancel grams, so this should be the conversion factor. All right, and that will cancel the gram, give you cubic centimeter, and then 0.895 divided by 0.504 give you 1.66 cubic centimeter. And next we want to change to milliliter, and we know 1 milliliter, 1 cubic centimeter. And since we want to cancel the cubic centimeter, so we put 1 cubic centimeter as the denominator. And that gives you final answer 1.66 milliliter. So this is an example using density as a conversion factor. In this case, we convert mass to volume. Now you can also convert volume to mass, and then you should use this one to cancel volume. You get mass, grams. Okay. Another thing I want to mention is that sometimes you can combine several steps together. For example, so this step give you cubic centimeter, so you can 0.895 gram times 1 cubic centimeter, 0.504 gram. By doing this step, you get a cubic centimeter, but without give you answer, we can multiply the second step, 1 cubic centimeter, 1 milliliter. So you can see here gram cancel, you get cubic centimeter, and then cubic centimeter cancel each other. So the final unit is a milliliter. and then use this number divide by 0.54 times 1, and that give you answer. So you combine two steps together, all right? That's also a common practice. We are all familiar with temperature. Temperature has different scales: Kelvin, Celsius, and Fahrenheit. Kelvin is the absolute temperature scale, which begins at absolute 0 and has only positive values. Celsius is based on the freezing point and the boiling point of water. So freezing point is 0 Celsius. When water freezes, the temperature is 0. When water boils, the temperature is 100. So in between, you divide 100, you get each degree of Celsius. Now, this is the temperature scale used most commonly around the world. Celsius and the Kelvin scale use the same size degree, although their starting point differ. So that means 1 Celsius equals 1 Kelvin, but their starting points differ. So for example, if ice melt or freeze, okay, then that temperature is 0 Celsius, okay, but at that temperature the Kelvin is 273.15 Kelvin, because Kelvin 0, absolute 0, is much below this temperature, 0 degree. So this is 0 Kelvin, all right? When the ice melt, the temperature in Kelvin is 273 Kelvin. Now each degree equals Celsius equals Kelvin. So they have the same size, okay? But the 0 is different, and therefore if you have a Celsius, you need to add this number, that is 273. For example, here, let's say this is 10 degree in Celsius. Then in Kelvin, you need to add this amount, which is 273, to give you Kelvin. Now, Fahrenheit scale is commonly used in US, and this scale has a different degree size and a different 0 point than both Celsius and Kelvin. So here are the relationship between Kelvin, Celsius, and Fahrenheit, as we just showed in the last slide. Kelvin can be calculated by Celsius plus 273.15, because 0 Kelvin is 273.15 degree below 0 degree of Celsius. Okay, and so Celsius can be calculated by Kelvin minus 273.15. Now the Fahrenheit and Celsius Celsius is quite different, because it has different size and different 0. So Fahrenheit can be calculated by 9 divided by 5 Celsius plus 32, okay, or Celsius can be calculated by Fahrenheit minus 32 and then times 5 divided by 9. Sample problem 1.8. A child has a body temperature 38.7 Celsius and the normal body temperature is 98.6 Fahrenheit. Does the child has a fever? And what is the child's temperature in Kelvin? So to find out whether child has a fever, we need to compare these two temperatures, but they have different units, so we need to convert Celsius to Fahrenheit and then compare with the normal temperature. If it is above it, then the child has a fever. Okay, so first convert Celsius to Fahrenheit. From last slide, we saw that Celsius to Fahrenheit is 9 divided by 5 times Celsius plus 32. Okay, that's the equation. So plug in this should be Celsius. Okay, so add Celsius here, and in this case is 38.7. You get 101.7 Fahrenheit, and this is greater than normal temperature 98.6, and therefore the child has a fever. Next, what is the child temperature in Kelvin? So to change Celsius to Kelvin, we need to add 273.15, and that gives you 311.8 Kelvin. Extensive properties are dependent on the amount of substance present. For example, the more substance you have, the more mass it has, and the larger the volume the substance is. And so mass, volume are extensive properties. Intensive properties are independent of amount of substance. For example, the density of water is about 1 gram per cubic centimeter. No matter how much water you have, the density remains the same. So the density is an intensive property that is independent of the amount of substance. Every measurement includes some uncertainty. The rightmost digit of any quantity is always estimated. For example, when you measure the mass of an object and you get, let's say, 51.2 grams, okay? The rightmost, this 0.2, this is estimated, okay? And therefore this is an uncertainty, okay? The recorded digits, both certain, so certain and uncertain, are called significant figures. In this case, you have 3 significant figures. The greater the number of significant figures in a quantity, the greater its certainty. Here shows 2 thermometers. One graduated in increments of 0.1 degree. The other one is 1 degree. Okay, let's look at the second one, and this is enlarged one to read the temperature. This is mercury, and so first let's look at the numbers. So 20 degree, 30 degree, 40 degree. In between you have 10. So each must be 1 degree, and that's why it's said 1 degree increment. All right, so let's read the mercury height. So here is between, so this is 2 and this is 3. So the height is between 2 and 3, and therefore the reading must be 32. So this is 32 point something. So we know it must 32 is certain, but the next one is estimated. Okay, because we know it's between 32 and 33. So 32 point something. Here we estimate 32.3. So the last one is estimated, is uncertain. We have 3 significant figures. 2 of them are certain, 1 is uncertain. Let's look at the left side. So this one, 31, 32. In between, again, you have 10, so each must be 0.1. Okay, that's why it says increment 0.1. Okay, and now let's look at the mercury height. And so here, mercury height is between, okay, so because each one is 0.1, so 32.01, so 32.1, so this is 0.1, 0.2, and so 0.3, and so this is between 0.3, this one, 0.4. Okay, so the reading is 32.3, 32.4. So we are sure it's 32.3. But the last one we have to estimate, and we estimate to be 32.33. Okay, the last one is again estimated, but the first 3 are certain. So in this case, we have 4 significant figures. 3 of them are certain. Okay, the last one is uncertain. Here are some rules to determine which digits are significant. First of all digits are significant. What's the exception? The exception is that zeros that are used only to position decimal points. For example, 0.01. So these zeros are used to position the decimal points. These are not significant figures. So this has only one significant figure, and it's this one, 0.52. So how many significant figures? Only 2. This is not. Okay, 0.00573. You have 3 significant figures. These zeros are all used to position the decimal points. They are not counted as significant figures. Next, zeros that end a number are significant. Okay, for example, 5.0. This is a significant figure because this one is not used to position the decimal point, because you can write as 5. So these two have same value, but they have different meaning. This one tells you this 5 is uncertain. Is uncertain. It's only one significant figure, but this one has 2 significant figure, and this is uncertain, and this is certain. 5 is certain. All right. So maybe 5.1, 5.2. So this is uncertain. This 0 is estimated. Okay, and therefore zeros and a number are significant. Okay, whether they occur before or after decimal. For example, 203.05. Okay, this is significant because this is not used to position the decimal. It's the number itself. So it is a significant figure, and this is a significant figure. If you add a 0, this is a significant figure. So this has 1, 2, 3, 4, 5, 6. 6 significant figures. Okay. Now, so 5300. Okay. Compare this one 0 and 5300. Okay. This has 5 significant figures. Remember, this 0 after decimal is a significant figure, and these are all significant figures. But this one, so only have 2. So these 2 are significant. No decimal. If no decimal point is present, 0 at the end number are not significant. So these are not significant. Okay. So these only have 2 significant figures. Sample problem 1.9. For each of following quantities, underline the zeros that are significant figures. SF means significant figures, and determine the number of significant figures in each quantity. So first, underline the zeros that are counted as significant, and then count the numbers, significant numbers for E to G. Okay, from E to G. Express each in exponential notation first. So our plan is we determine the number of significant figures by counting digits. Pay particular attention to the position of 0 in relation to the decimal point, and underline the zeros that are significant, using the rules we mentioned in the last slide. Let's count the significant figures. Let's look at A. The first 3 zeros are used to position the decimals, so they are not significant. And the last one is a significant figure, and therefore in this number you have 2 significant figures. Okay, the last 0 is significant. In B, this is used to position the decimal. This is not. The second 0 is included in the number, and therefore the 4 digits are significant. Okay, so you have 4 significant figures. In C, so this one doesn't have 0, and sorry, this doesn't have a decimal, but this 0 is included in the number, therefore it's significant. And so we have 1, 2, 3, 4, 5 significant figures. In D, we don't have decimal, so the ending 0 is not counted as significant. The 0 in between is a significant figure, so we have 3 significant figures. In E, all these zeros are decimal points, okay, to position the decimal points, so they are not significant figures. So we have 4 significant figures. Now to write the scientific notation, we only write a number from 1 to 10, and so you cannot write 4,715. Instead, you should write 4.714. It must be between 0 to 10, and this number is between 0 to 10. And then you times 10 to a certain power to represent the decimal. So here we have 1, 2, 3, 4, and then 5. So 5 numbers after 0, and that must be -5. Okay, so this is the scientific notation, and this is you have 4 significant figures, and that's here. Okay, next one, you have a decimal. Note that you have a decimal here, so these are significant figures, and they are not used to position the decimal. And we have 1, 2, 3, 4, 5 significant figures. They are all significant. To write scientific notation, we write 0 to 10, so 5.70600. This must be included because they are significant figures. And then times, and to determine the power, you need to count the numbers before 0, so before decimal. 1, 2, 3, 4. Okay, so 4 after 5, so 4, so 4 power 4. Okay, so 10 to the 4th power, and we have 5 significant figures, and the 2 zeros are significant. Okay, next one, these are all used to position the decimal. They are not significant figures, and this is a significant figure. So we have 4 significant figures, and so this is similar to E, and so we write 7.160 times 10 to the count number after decimal. 1, 2, 3, 4, 5, 6, 7. So it's -7. Okay, so -7 and 4 significant figures. Let's now look at the rules for significant figures in calculations. Rule number 1. In multiplication, division, the answer contains the same number of significant figures as there are in the measurement with the fewest significant figures. Okay, so here we have 3 measurements: 9.2, 6.8, 0.3744. Okay, we want to calculate the multiplication. Okay, so first, ignore the significant figures. Use your calculator and just calculate the multiplication. So here is your answer, 23.4225. And then you need to decide how many figures are significant. Now, because you have a measurement that only have 2 significant figures, and this one is 2 also. This one is 4. The answer cannot have a significant figure more than the fewest one, which is 2. So not all of them are significant, only 2 of them. And therefore, the ending numbers are not significant. So the answer should be 23, okay, because those are not significant. You can only have significant figures as the fewest one in the measurement. Rule number 2 for significant figures in calculations. For addition and subtraction, the answer has the same number of decimal places as there are in the measurements with the fewest decimal place. Okay, so compare with number 1, rule number 1. Number 1 is about fewest significant figure. Here is the decimal place. Okay, so let's look at the two examples. If we add these two measurements, measure the numbers, okay, so what is the answer? All right, so first, again, ignore the decimal or significant figure, just calculate using your calculator, and this is your answer, 106.78. After your calculation, now you decide, okay, what is the final answer? All right, because it's addition, so you should have decimal place as the fewest decimal as the measurements. Okay, so let's look at the two measurements. Here, this is the decimal. After decimal, you have 1. Okay, here you have a decimal, you have 2. So the fewest decimal place is the first number. You only have 1. Therefore, here, okay, you only keep 1 decimal place. Now, because the last number is 8, 8 is greater than 5, so we need to round off. You need to add 1 to the one before it, and so the final answer should be 106.8 instead of 7. Okay, next one. Okay, subtracting. So same rule. We calculate using calculator, and this is the answer. And then we look at the decimal place, and this has 1, and this has 1, 2, 3, 4. Okay, and therefore you need to keep the fewest one, which is 1. So again, you keep here, and because 8 is greater than 5, so you add 1 to 0, and you get 863.1. Okay, so remember, for plus minus, you look at the decimal place, okay, with the fewest decimal place in the measurements, the same. If it's plus multiplication or division, then you count the significant figures should be as the same as the fewest significant figures as the measurements. As we have seen from last few examples, sometimes we need to round off numbers, and here are some rules for rounding off numbers. Okay, now if the digit removed is more than 5, then the preceding number increases by 1. Okay, so for example, this 5.379, we want to round off to 3 significant figures. So here is the 3 significant figures, and the number after it is 9, which is greater than 5, and therefore the one before it is 7, needs to add 1, and so it gives you 5.38. If the digit removed is less than 5, then the preceding number is unchanged. Again, this number needs to round off to 3 significant figures, so you want to go to here. All right, 3 significant figures, and we look at the one after it, which is 3. 3 is less than 5, so the one before it is retained, so the number should be 0.241. What if the digit you want to remove is 5? Okay, so if it is 5, then it depends. Okay, it depends on the number before it and after it. If the number after, okay, if this is the digit you want to remove, but if you have a non-zero number after it, then you definitely want to add 1 to the number before it. So if this is 4, okay, if you want to, okay, let's say you want to go to 14, and 5 is need to be removed, and because you have 1 after it, so you need to add 1 to 4. Okay, so for example, here is a number, and you want to round off to 3 significant figures. So that's the one you want to go. And the one you want to remove is 5. But you have 1, 3 after 5. And therefore, the one before precede the 5 should add 1. And therefore, the answer is 17.7. But what if there's no number after 5 or 0? Okay, if there's no 0 or no number, or if it's 0 after 5, then you have to look at the number before it. For example, here, this is the number you want to round to, again, 3 significant figures, so it's right here, and therefore you want to remove 5, and there's 2 zeros after 5. So at this point, you have to look at the number before 6. So here, before 5. Because the number before 5 is 6, and 6 is a even number. So if it's an even number, then the number should be retained, and so you don't need to add 1. So the answer is 17.6. On the other hand, here is a number. You want to, again, go to 3 significant figure here. You want to remove 5, and there's no number after 5, and therefore you need to look at this number before 5, which is an odd number. If it's an odd number before 5, then you need to add 1, and so it's 17.8. Okay. On the other hand, let's compare this one. You want to go to 3 significant figure. So here is the position you want to go. You want to remove 5. Again, there's no number after 5, and so you look at the one before it, and it's an even number. And the even number, you don't add 1, and therefore it is 17.6. Okay, so again, if you want to remove 5, you look at, do you have any number after 5? If you have non-zero, for example 2, then you need to add 1 to the one before 5. Okay, if you have 0 or no number, then you need to look at the one before it. If it's even, you don't add any number. If it's odd, you add 1. When performing calculations, you need to be sure to carry 2 or more additional significant figures through a multi-step calculation and round off the final answer only. The measuring device used in the laboratory determines the number of significant figures possible. For example, when you use this analytical balance to measure the weight of a sample, and you get 6.8605, so you have 1, 2, 3, 4, 5 significant figures and 4 decimals. Okay, so the last one is uncertain. 5 significant figures. Now, if you use a graduated cylinder like this one to measure the liquid volume, and you can read 68. So here is 68. And then the next one you need to estimate, for example, 68.2. So this is uncertain, and you have 3 significant figures. So in this case, the graduate cylinder has less significant figures for the measurements than this analytical balance. There are numbers that have no uncertainty, and these numbers are called exact numbers. For example, there are some definitions. 1 gram is 1000 milligram, 1 hour 60 minutes, 1 inch is 2.54 centimeter exact. These are the definitions. There's no uncertainty. These are called exact numbers. Okay, they are not significant figures. And the other one is counting numbers. For example, there are 20 letters in alphabet, and these are counting numbers. They are significant figures. Okay, no uncertainty. So there's an important property for exact number, and that is they do not limit the number of significant digits in a calculation. For example, when we perform multiplication, for example, if 1.2 times 3, that gives you 0.6. Now, if both are measurements, then the fewest digit significant is 1. So this is 1, and therefore the answer should round to 4, because the answer should have the fewest significant number as the measurements. So that's the answer. However, if this is an exact number, it's a counting number. So for example, 3 people, each people 1.2 for example inch or some meter, then when you calculate, this doesn't count as the fewest significant figure. So you calculate this one, which is 2, and therefore the answer should also have 2. So this will be your answer if this is your is the exact number. Sample problem 1.10. Perform the following calculations and round each answer to the correct numbers of significant figures. So our plan is we use the rules for rounding presented so far, and we subtract before we divide. And note here there's a definition: 1 gram 1000 milligram conversion factor, and this actually is an exact number. Let's begin with A. In A, we need to do the subtraction first and then division. Okay, we can use a calculator first, do the subtraction. So the answer from calculator is 14.9041. Now we need to decide significant figures or decimals. Because it's subtraction, okay, the rule is for addition, subtraction, we need to look at the fewest decimal. So the first number has 4 decimal, second number has 3, and therefore the answer should also have 3 decimals. So it should go to this number 4, and therefore we need to remove 1, and the answer is 14.904 divided by 7.085. Okay, and now use the calculator. Okay, the answer from calculator is this number, but we need to decide the significant figures or the decimals. So the rule is for multiplication, addition, division, we look at the fewest significant figures. So the first number has 1, 2, 3, 4, 5 significant figure. The second number has 4. Therefore, we should have 4 significant figures. So 1, 2, 3, 4. So should go to here, and 5 should be removed. And because there's a non-zero number after 5, and therefore the one before it should add 1, and the answer should be 2.104. Okay, the unit calculation just like numbers. So here you have centimeter squared divided by centimeter. So 1, 2, the power 2 minus 1 give you 1. Okay, so that's question A. Now let's look at question B. In question B, first multiplication. So this number multiplied by this number, and then division. Okay, now in multiplication, here the second number is an exact number because 1 gram is exactly 1000 milligram. That's a conversion factor. So because it's an exact number, it does not affect the significant figures. And so for multiplication, we look at the fewest significant figure. So we look at this number because exact number doesn't limit. So so when you calculate 10 to the 4th power divided by 1000 give you 10. 10 times 4.8 should give you 48. Okay, but because the first number has 3 significant figures, and so the calculation should also give you 3 significant figures. So how do you write 3 significant figures for 48? Well, you need to add 0.0. Okay, so the value is same, but now you have 3 significant figures. 0 after point is significant. Okay, so the answer here is 48.0 divided by 11.55. Now first use a calculator. this is the answer from calculator. But for division, you look at the fewest significant figure. So here you have 3, and here you have 4. So the answer should have 3 significant figures. So goes to this number, 3 significant figure. You need to remove 5, and because you have a non-zero after 5, and therefore you need to add 1. Okay, so the answer should be 4.16 gram per cubic centimeter. Here are some important concepts when perform measurements. One is precision, one is accuracy. Precision, also called reproducibility, it refers to how close the measurements in a series are to each other. Accuracy, on the other hand, refers to how close each measurement to the actual value. For example, if the actual value of a water sample has a volume, let's say 25 milliliter, and if you perform several measurements and you get 27.3, 27.2, 27.4, 27.3, and you can see they're very close to each other, and therefore these are good precision. So this has a good precision because they are very close to each other, but they are far away from the actual value, so it's not accurate. The accuracy is poor, but they are good precision. Okay. Now there are two types of errors. Systematic error, which is usually due to the instrument. Okay. If the instrument is not calibrated well, okay, it doesn't perform well. So every time you give you an error that always higher, okay, than the actual value, or sometimes every time you measure it, it gives you a lower value. Okay, so if you have a systematic error, and sometimes it can have a good precision, the values, for example, in this case, every time it is higher than actual value, but they are very close, and this may be due to the systematic error. Okay, the random error produce values that are both high and low. So sometimes high, sometimes low. It's random, and random error has many factors. It can be due to the person's skills in performing the experiments. Okay, not very good. Sometimes do get a higher value, sometimes get a low value, or maybe because of temperature fluctuation in the room, so you get random errors. This diagram shows the comparison of precision and accuracy. So the actual value for the mass is 25. This is the actual value, and the 4 measurements here are very close, also close to the actual value. So this measurement is precise and accurate. Okay, precise means they are close to each other, the measured value, and accurate because they are close to the actual value. All right. Now, and the second experiment, so 4 of them are close to each other, so good precision, but they are far away from actual value, so not accurate. Okay, good precision but not accurate. So in this experiment, the 4 experiments have random errors. Okay, sometimes low, sometimes high, and so you have low precision. Precision means they are close to each other. These are not close to each other, so low precision. But if you average them, you see this is below the actual value. This is higher, and this is higher, this is below. So if you average, these cancel each other, give you quite accurate. Okay, so the average value can be accurate, but it has low precision because you have random errors. The last one, they are not close to each other, so it's poor, low precision, and they are far away from the actual value, and therefore it's low accuracy. So low precision, low accuracy, and this is due to the systematic error because they're all above the actual value, and also they have random error. Okay, it's high, low, okay, so both systematic error and random error.